Started. Welcome to Thursday. It is Thursday of week 5, which means that we are like a little over a third of the way done with the semester, which is wild. But we have a couple things coming up here in thermo over the next little bit that I wanted to point out. For this class, so this is week 5. Here's the Moodle page for week 5. There's a quiz coming next week. So watch out for that next week, Thursday. It's going to be, I guess it's a little bit different because the first 2 quizzes that we've done so far, I've given you like a practice quiz. This one, I don't have a practice quiz, but these 3 bullet points right here kind of describe the types of questions that could be asked. Just know when you're reading that, this is going to be a 15-minute, 15-point quiz. So I can ask, there are going to be multiple questions. So each of the questions is going to be a simple calculation. You're not going to have to like solve a homework problem and do 3 of those in 15 minutes. So they're going to be relatively short, trying to just make sure that I guess like conceptual stuff that we've covered most recently about second law and efficiency, things like that. So that's what the quiz is going to be on. The last bullet point, there will be a multiple choice question about reversible processes, right? So a reversible process is, we're really interested in that because that's the ideal, that's the best. It's going to be a process where your whole system is in equilibrium the entire time. And if you went forward and went back, there is literally no change to the entire universe, right, from an entropy perspective. So a reversible process, I'll give you examples of like real things, and you have to tell me, is that pretty close to a reversible process or is it like way far away? And it should be, if you, I'm not going to have some that are like really close and some that are a little bit close. Like it's either going to be pretty close or it's going to be really far away for that multiple choice problem. The other stuff that's a little bit different for this week, we're going to come in next week and I'm going to assume at the start of class that you have seen 2 things. So normally we like, I know how this goes. When I have homework due Thursday at 9 p.m. Most of you haven't started it or you've looked at it a little bit, but it's not done yet. That's fine. Next week, though, we're going to kind of jump in a little bit on stuff that you should have seen in the homework. So I have specifically 2 things. The last problem on homework 5 should be done when you come to class. It doesn't need to be turned in, and you just need to have done it. If you haven't, we're going to talk about a whole bunch of stuff and you'll be like, I haven't seen that yet. What are we talking about? So make sure you're done with the last problem on homework 5. And the same thing, kind of before you start that, you should have gone through the participation thing. So that's another thing. I have the due date for that at class time. So you should have done that. That's relatively short. It shouldn't take that long to go through. But make sure you've worked through problem 5. It's a little bit, it's probably the, like you can jump in straight into the homework and just do problem 5. I recommend just finish the homework before class. But you'll have to adjust your kind of normal weekly schedule at least a little bit. Because we'll jump into class next week, assuming you all have seen that and have worked through it, and then we'll kind of work on top of that same problem. So that's the only, I guess that's the only big change from kind of a normal week in thermo. So other things should look hopefully relatively similar. Okay, so come on, buddy. There we go. So if you remember what we were talking about at the end of last class and what you've hopefully seen a little bit in the homework or what you're going to see very soon in the homework is this type of efficiency that we call isentropic efficiency. We went through this example in class. We said a turbine is operating. It's not an ideal turbine. It's a 70% efficient turbine. And we went through and had we calculate like how much work did we get out of this. And we also calculated how much entropy is generated. And we can go through and we can kind of math our way through that and get all the answers and numbers. I just wanted to talk a little bit about a way to hopefully help you, especially for those of you who are more visually inclined, kind of think through a way of thinking about what's happening, and in kind of a framework, I'll call it, that we're going to continue to use and think about for the rest of the semester. So a nice conceptual framework for thinking about that problem is on a phase diagram. We're going to use a temperature entropy phase diagram, and for some reason it's still trying to make me present PowerPoint. There. Okay, so we're going to use a temperature entropy phase diagram. And on a temperature entropy phase diagram, the phase boundary looks something like this. Right, where up here you have your critical point. Right over on the left side of that, you would have liquid. Underneath the curve, you have a boiling mixture, vapor-liquid mixture, and to the right of the curve, you have a gas. It's useful if we go back and remember what we're trying to do. Okay, so in this, we're going to basically picture this process happening on the phase diagram. So what's happening? So we're coming in. We're coming into the system at 500 degrees Celsius and 500 kilopascal, and we're leaving at 100 kilopascal. So we have a temperature entropy diagram, but we're dealing with pressures, so it would be good to know what pressure looks like on this diagram. So if we put lines of constant pressure, what those will look like is a really steep line in the liquid phase. Right, so as we increase pressure of a liquid, entropy increases very slowly as we increase temperature. So entropy increases very slowly. Then temperature and pressure are constant, but entropy is increasing while you're boiling. And then, so that should do a better job. That should be, oh no. Come on, buddy. Okay. So that should be exactly a horizontal line. And then it kind of loops up after you're a gas, where temperature and entropy are going up, both at constant pressure. So this is P, we'll call that P2 equals 100 kPa. And the other pressure that we're interested in is 500 kPa, and that might look something like this. P1 equals 500. Okay, so that's what lines of constant pressure look like on this type of a phase diagram. You could go back and look at your steam tables and kind of convince yourself that this is true. If you go, at constant pressure, if you go up in temperature, you can see how entropy changes, and right, you could build a graph like this just from the steam tables. Okay, so what's happening? So we're coming in. I'll switch colors. We're coming in. Our inlet phase is right here at 1. So if we go, that would be at 500 C. Right, if we kind of carry that across. So we're coming in at 500 C and 500 kilopascal there. In the ideal turbine, right? To solve the real one, we first had to solve ideal. The ideal turbine is going to go from 500 kPa and 500 C initially down to 100 kilopascal. And it's going to do on this, it's going to be a delta S equals 0. So it's going to be a vertical line because S is not changing. So it's going to be, so this is, we'll call this 2 ideal. It's going to be exactly vertical because delta S is not changing. If we had a, if we remember back, this temperature, if we were to take this guy back to the y-axis, this was 264 degrees. Okay, so that's what we're doing. We're going up from 500 and 500 down to 100 kilopascal and 264 degrees. Our real turbine is only 70% efficient. So we calculated, when we were doing our calculations, we were calculating a change in entropy, right? Delta S, it was positive because it was a possible system, a real system. So what that would look like is we're going to be still going from 500 down to 100 kilopascal, but we're going to be going to the right on the entropy scale. So we're going to be going down, but we're going to be moving always to the right, to the right, to the right, and we're going to crash into it. Well, I can draw that maybe even a little bit more pronounced. We're going to go down and maybe be somewhere over here. Okay, so we're going to still go from that 500 kilopascal line down to the 100 kilopascal line. We're just going to be moving to the right as we do that. Let me erase that dot. Okay, and then if we took this over, then our temperature here would be 336 degrees Celsius. Okay, we're going to continue to look at temperature entropy diagrams, and we're going to do that because, well, there's more that is useful about them in understanding kind of how processes are happening and kind of visually seeing how we would make a change to a system to improve the performance, or how some change would hurt the performance of our system. So we're going to kind of put this on hold, but hopefully that gives you some sort of a picture of how the real process and the ideal process are similar but different, kind of on a more visual perspective. Okay, so we're going to do something that you're probably going to get sick of hearing me talk about, and that is, yikes. That is, think about the second law. We've been talking about the second law a lot. We'll continue to talk about the second law because the second law is the fun one. The first law is, like, once you hear it, I don't know, for like one class, we've kind of covered it, right? Energy is conserved. You guys have already done conservation of mass. You've done a lot of conservation of mass stuff. It's just a matter of, like, you know, kind of the accounting for how do you take one form of energy and turn it into another. You don't need to write this whole statement down. We'll write like a little summarized version. This is a statement of the second law that's from our book. It's the one that we've used most often. Okay, so it's called the Clausius statement. It is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a cooler body to a warmer body. Right, so this is our statement that well, I guess how this is written, heat can't flow cold to hot. Okay, so that's the Clausius statement of the second law. That's the one that we've talked about the most, but we've run into at least one situation where it wasn't obvious that that was what we were breaking. So if you remember back to this nozzle that took steam in and shot liquid water out at 5,000 miles per hour, do y'all remember that? And we said, there's no way, like, you have low pressure steam coming in and you have a liquid jet of water at 5,000 miles per hour. There's no way that's possible. And I agreed, and the second law agreed. We calculated what the change in entropy was. The change in entropy was negative. And I said, really what happened is we broke the second law, which is kind of this: heat can't flow from cold to hot. But thinking about like what's actually happening in that process, right? Like steam coming in and liquid water coming out, it's not clear that we broke that, right? At least it's not clear to me. Like they're a little bit different. There's another version of this, another definition of the second law. These came about independently, and it was only after some time that people realized that these are kind of the same thing. The Kelvin-Planck statement is, it is impossible to construct a device that will operate in a cycle and produce no effect other than the raising of a weight, work, and the exchange of heat with a single reservoir. So a kind of better way to say this, or what I think is a better way to say this, heat can't be perfectly converted to really mechanical energy. Like work or kinetic energy, really it applies more broadly than that. But
when you say heat can't flow cold to hot, is that the same unless there's something that's making it?
Yeah, you have to, it can, but you have to add something else to the system. You have to add work to the system. And we'll talk about, we'll kind of mention that. We'll draw us out some pictures that hopefully will help explain kind of in diagram form what they're talking about. Okay, so there are these two kind of competing definitions. And we've run into, I mean, the first one seems just so obvious that it's a little painful. The second one isn't as obvious, and it's certainly not obvious that the two are the same. So we're going to dig into that a little bit. And we're going to dig into that by looking at some, or by drawing some diagrams. Okay. So I'm just going to, as kind of shorthand in this, you don't have to remember like the Clausius statement of the second law was this, and the Kelvin-Planck statement of the second law was this. But I'm going to use those as kind of shorthand for these two competing definitions, at least like in the context of the next little while. So the Clausius statement, what Clausius said was, okay, if we have something like this, something hot, and I'm just going to make a note, this is a thermal reservoir. It's a nice, not actually real, but nice conceptual tool to think about. It's a body to heat can transfer. So we can take heat and put it in or take it out without changing temperature. Okay, so it's another term that's sometimes used as like a heat sink. Like we can put heat in, we can take heat out. It's a thermal reservoir because we can get as much heat as we want, but it doesn't change anything about the thermal reservoir. So like a relatively close approximation to that would be like anything really big. Like the ocean is a pretty good one. A river is a pretty good thermal reservoir. The atmosphere is a pretty good approximation of a thermal reservoir. Okay, something like that, something that's large, at least large in the context of how much heat you're putting in, right? The ocean, obviously, you put in enough heat, it does change temperature, but that's a lot of heat. So for a lot of systems, practically it acts as a thermal reservoir. Okay, so not to get too distracted. So we have something hot, and down here at the bottom, we have something cold. Okay, and what Clausius said was we can't have some black box here, which is operating in a cycle. I'll put like a little cycle-y arrow in the middle. Think about when we're talking about a cycle, we'll see processes that are acting in cycles, and that will help make it clear. But think about when you were in intro lab and you did the refrigeration lab, and you went and you took temperatures at different points. There was a fluid, a refrigerant that was flowing around and just kept going around and around and around through all of these different things back and forth. That's a thermodynamic cycle. So you're taking one thing and you're just passing it around and around and around in the loop. You can't make something like that. I don't know what components it has, it doesn't matter. But you can't make something like that that takes heat from this cold place, we'll call it Q cold, and pushes that heat into the hot thing. So heat doesn't flow from cold to hot naturally, but you can't make something that forces heat to flow from cold to hot. We'll just say there's no, that the work input is equal to 0, just to kind of, clarify that we didn't plug this thing in. So if you don't plug it in, that can't happen. You can't make some contraption that forces heat from cold to hot. Okay, so Kelvin Planck over here is saying something different than that. What Kelvin Planck is saying is you can't take heat, again, from a thermal reservoir and take that heat into your black box contraption. Again, it doesn't matter what it is, it's something, and convert that heat. So we'll call, say, the amount of heat that you took from the high temperature reservoir, the hot reservoir, QH, and you can't take that and convert it directly into work, right? Where the work would be equal to the magnitude QH. Okay, and I will argue here in a few seconds that those two things they're not the same thing, but they're part of the same thing. So I think drawing it as pictures like this helps us maybe at least see that. Hopefully you'll at least get to the point where you're like, okay, maybe. And then we'll kind of leave it and not deal with it too much anymore. But okay, so let's draw now a new picture of, okay, let's say we have a high temperature thermal reservoir. We'll call it T hot and T cold still. Let's put over here, let's put the Clausius definition. So you have QC, and you have work, no work input. Okay, and over on this side, we're going to have a second process happening where we take heat from that hot reservoir and then we lose some heat to the cold reservoir. It's supposed to be a C. Okay, the amount of work that we're getting out over here by an energy balance would be equal to QH minus QC, right? Because energy balance, what goes in must come out. And if we look at some, right, this is now a drawing with two different kind of subsystems. If we look at it and we look closely enough, it should be fairly straightforward. Like this part here, that part is Clausius. That's the heat can't flow cold to hot. This part is Kelvin Planck. Right, if we remember back, Kelvin Planck said that we can't have a black box that takes heat from a high temperature reservoir and turns it directly into work. And the reason that we can't is because, right, if you look at this black box, what's in green, that's our black box. So the only way to do Kelvin Planck, take heat and turn it directly into work, we're going to take heat, turn some of it into work, and we're going to lose some of it. The amount that we lose is that, QC. So we turned some of our heat into work, and we lost some to a cold reservoir, TC. Then Clausius over here said, aha, but I can make heat flow backwards. So then it took that heat and pushed it back up into the hot reservoir and allows the cycle to go back. So again, you don't need to be too worried about remembering all of this, but hopefully at least this gives you some concept that these two things are related, that the only way that you could perfectly turn heat into work is if you could make heat flow backwards. Like that's the necessary condition. If heat could flow backwards, then you could perfectly turn heat into work with some setup like this. Okay, so that was fun, at least for me. But it's talking about different things that we can't do. So it's a natural next question. Is what can we actually do? Okay, so we're going to look at two different processes that we can actually do. One is going to be somewhat similar to Clausius, and one is going to be somewhat similar to Kelvin Planck. I'm going to at least call them for right now. This one is the Clausius-like part. Again, you don't need to remember the Clausius and Kelvin. You don't need to remember the names. But that's just kind of shorthand for referring to them for right now. So what this said is we have a hot reservoir. Down here we have a cold reservoir. We have some black box, which is operating in a cycle. And what Clausius wants to do is take heat from our cold reservoir and pass that heat up into our hot reservoir. And that can't happen if there is no work input. So what can we actually do? Well, we can put in some amount of work that's not equal to 0. Right, so our high temp is gaining heat in this system. Another way to think about that, our low temp is losing heat, right? This is this is a refrigeration process. But we need, for a refrigeration process, this needs a work input, right? For any refrigerator to work, it has to be plugged in. So that's the Clausius-like process that we can actually do. And we'll talk about what actually has to happen in the black box to get that to work. Okay, the Kelvin-Planck-like process right, what Kelvin-Planck wants to do is have a black box which takes heat from a high temperature reservoir, QH, and turns that into work. We can't do that. We can't turn heat directly into work, but what we can do is we can take heat, we can turn some of it into work, and then we waste the rest of it. So we can take heat, we have a heat input into the system. We can take some of that heat and turn it into work. And we're going to lose some amount of heat. We call it the waste heat. We're going to lose some of heat to a cold reservoir. Think about, okay, a real process like this. Say a car engine, we're all familiar with those. We have an explosion inside where we burn gasoline, that's our source of heat. We turn some of that into work, pistons move, your car moves, and then the hot gases go out the exhaust, right? Your exhaust is still really hot. That's what's happening. So you're taking some of the heat of combustion, you're converting some of that into work, and then you lose some of that heat out of your exhaust. The Kelvin-Planck-like one, we call this at least generically, we call it a heat engine. And what we'll see is we're going to spend a fair bit of time initially talking about heat engines, and we'll kind of hold off on talking about refrigeration stuff for at least a little while. You'll have one homework problem coming up fairly soon, I believe. Maybe that's refrigeration. I'll have to double check again. But we're going to spend most of our time in class talking about the heat engine side of things, just in part because the refrigeration side of things, you go, oh, that's actually basically exactly the same. It just goes backwards. And that's what we'll find is, right, all of the analysis and stuff, it's a little bit different, but it's basically the same for the same reasons. It's just backwards. So we'll spend most of our time on the right side of this, on the heat engine side. If you have, does anybody have one of these printed out? I would imagine not. I'm going to pass these out. So kind of like we did, well, I'll wait a second to chat, but we're going to spend a little bit of time just thinking about what the ideal process would look like. Everybody has one? All right. So let me pull up the sheet that you just got. Okay, so this page, right, if we want to think about, we're going to kind of do the same thing that we did when we talked about isentropic efficiency. Right? If we want to understand the operation of a real turbine, first we should understand an ideal system, and then we can kind of compare the ideal system and the real system, and we can do some of those same kinds of things. We're going to do it, it's a little bit more complicated for heat engines, but we're going to first start with an ideal heat engine. And really, if you think about what we're trying to do, we just go back to the pictures we just drew. We're trying to see, like, that black box, what's actually inside? What should we put inside that black box? So if we want to say, well, what's the best that we could do? What's the best black box that we could make? The best black box that we could make is the Carnot cycle. So that's what we're going to start by talking about. We're going to talk about what's this? It's not a real black box, right? It's a theoretical system because it's the best that we could possibly do. But we're going to say, okay, what's in the Carnot cycle? What's inside of that black box that would be the best possible way to turn heat into work, or the best possible heat engine? Well, the first thing that, if we're like considering best possible, so one thing that we should note is that in a Carnot cycle, by definition, all processes are reversible. So circle that. It's already bolded and italicized, but right, this is the ideal system. This is the ideal system. So everything that we do must also be ideal. That's kind of the idea behind that. Inside of our ideal black box, inside of our control volume, we have 4 different processes that are happening. I kind of outline what's happening in each of these processes, but we're going to start, we'll start with this. Okay, so if we go from here at state 1 up to state 2, what just happened? Well, it says process 1, 2. So just to, I guess, be a little bit more clear, right? When we were doing this on a homework, and I told you to solve this one piece of equipment, you'd have an inlet, which you called 1, and an exit that you'd call 2. We're going to do the same thing. So 1 is the inlet for this piece of equipment, 2 is the exit. And we're saying what happens between 1 and 2. What happens between 1 and 2 is that the gas is adiabatically compressed, right? But because this is Carnot, that's adiabatic and reversible. So that is this is a compressor. And this is a delta S equals 0 process, right? It's adiabatic and reversible compression. That's a delta S equals 0 process. From 2 to 3, right, as we go across the top, the language here is a little bit goofy. But if you think about what the language means, so the gas in state 2 expands isothermally due to the transfer of heat, QH, from a hot reservoir to the gas. So we have an isothermal constant temperature expansion. There are different ways that you can do this, but if we think about a normal way to do this, quote unquote normal way, would be boiling, right? Boiling happens at constant temperature, but you go from a liquid, which is a small volume, to a gas, which is a big volume, and the temperature doesn't, right? The temperature, it just is changing in volume. It's an expansion. So this is a boiler. And the temperature, here, I'll zoom in a little bit so we can see that better. So that's a boiler and the temperature is constant. For process 3 to 4, we're gonna have an adiabatic reversible expansion. So as we go down this way, this is an adiabatic reversible expansion. Adiabatic and reversible, you should immediately be thinking that's a delta S equals 0 thing. So this is a delta S equals 0. And an expansion, we would be talking about a turbine. Okay, so we have a compressor, then we have a boiler, then we have a turbine. The last step from 4 back to 1, the gas in state 4 is compressed isothermally. Again, the language is a little weird due to the transfer of heat QL from the gas to a cold reservoir. So the gas is, or the fluid is losing heat to our cold reservoir, and it's being compressed. So the volume is getting smaller and smaller and smaller, but the temperature is not changing. So this is a condenser, right? It's going from a gas or mostly vapor down to a liquid. And we're doing that by taking heat away. So this is, again, a temperature, a constant temperature process. All right, so if we look at kind of this system as 2 halves, right? The cold reservoir is at some temperature. We've called it before T cold. The hot reservoir is at some temperature. We've called it T hot. To get from 4 over to 1, that was a constant temperature process. This is an ideal process, so that means that is happening at exactly the same temperature as our thermal reservoir. Right? Those 2 temperatures are the exact same. So the entire bottom of our system, this is all at T cold. Right? 4 and 1 are both at T cold. And the same thing for the top. Right, this is all at TH. Okay, so you can kind of divide a Carnot cycle where the top half of the system is at the hot temperature and the bottom half of the system is at the cold temperature. So often when we're talking about a Carnot cycle, those 2 temperatures are the things that we use to define the system, and we'll see why fairly soon. Okay, but those 2 temperatures, the temperature of your hot reservoir, the temperature of your cold reservoir, those are kind of defining what the temperatures are in your system. Okay. So we're going to think, if you flip over, we're going to picture this on a temperature entropy diagram, kind of like, right, this is the same diagram that we drew right at the beginning of class. We said, let's picture a turbine, an ideal, and a real turbine on a temperature entropy diagram. So if we think about what's happening between 1 and 2, that was back up here, that's our compressor. So an ideal compressor has to be a delta S equals 0, so that's a straight line. And we're going from the cold temperature up to the hot temperature. So that's a straight line here up to 2. Now from 2 to 3, we stay, that's our boiler. So we're expanding, we're getting to higher volume, but our temperature is not changing. So we're going to be still on that temperature line, TH. We're going to be expanding, and our entropy is going to be increasing. So we're going to go over here to 3. From 3 to 4, that's a turbine. Again, it's an ideal turbine because everything is ideal in Carnot. So we're going to go 3 straight down to 4. And then from 4, we're going back to 1 because we go back to where we started. And we go this way. There are a couple things to note, right? So I told you this is an ideal system. So what that means is all of the processes are ideal. It should also mean that once it's done, right, an ideal thermodynamic system means that nothing has changed in the whole world. So that means if there was entropy generated in one step, it should be like reduced in the other step so that the total change in entropy is 0. That's what an ideal system means. So we have a delta S here from 2 to 3. S is increasing, entropy is increasing, but from 4 to 1, it decreases by exactly the same amount. So we get this nice little box shape. If you remember nothing else about Carnot, you probably, I hope you remember this, that it is a nice box on a temperature entropy diagram. Okay, and there will be reasons, especially when we start getting into things that are not Carnot cycles, why it's helpful to then picture it on a TS diagram. And remember, Carnot's a box. So the closer we are to a box, the closer we are to Carnot, the better we should be. Okay, so we have this box. If we go, okay, so part C, lightly shade in the area on your graph which corresponds to the value QH. So for a reversible process, right, Q was equal to the integral of T ds. So with temperature constant isothermal, Q equals T delta S. So we can think about that graphically because, right, T delta S, that's Q equals T delta S, area equals base times height. So the value of QH is base times height, right? This difference here, this side length is, that's delta S, right? That's the difference in S between state 2 and state 3. And then the vertical side length, that length is temperature. I'll make a little bubble. So that assumes that our x-axis is at 0 Kelvin, right? I have here that our y-axis is in Kelvin, and I'll just make a note. For entropy, for anything that you're doing with entropy, you have to use absolute temperature. You have to use Kelvin, or right, the Fahrenheit equivalent of that is Rankine, where 0 is absolute 0. And we'll come up against that a number of times. Like the rule of thumb is, if you're ever confused, use Kelvin and you won't get it wrong. If you're using Celsius, you might get it wrong. If you use Kelvin, you won't get it wrong. Okay. Then the last question, now shade in the area on your graph which corresponds to QL. That's again, Q equals T delta S. So you can see that QH, the amount of heat we put in, is bigger than QL, the amount of heat we lose. The difference is the side, the center of the area of the box itself, right? So the area of the box itself is equal to the amount of work that you're getting out of this Carnot cycle. Okay, we're going to talk, or you'll hear me talk more about heat engines and Carnot cycles and how we measure the efficiency of these and some of those different processes. We'll go back over some of this exact same stuff, but it's important enough I wanted you to see it twice. That's in the recorded lecture video for this week. The other stuff, just to remind you of again, the homework is going to have to be a little bit different for next week because you have to make sure you finish problem 5 at the very least before you come to class, or at least come with enough of it done that like you can talk to me about any questions you have in class, because we're going to be kind of building off of that problem for the next lecture. So with that, thank you all for coming. Have a great Thursday. And I'll be hanging around a little bit if there are any questions.